we'll have small derivation of Bayes theorem, which can be applied for a most general case of the sample space. This we have already seen, like all these events B1, okay, right here. So all these events B1, B2, and so on, Bn are mutually exclusive. So this is what we have the information. And also there is an event A. There is an event A that is occurring in the sample space S. Okay, this is the information we have. And now we are trying to get the expression for the conditional probability, and that too giving the concept of Bayes theorem. Okay, so this is what the expression we need to prove for a most general case of a sample space S, which is divided into n number of events, and there is an overlapping event of A. So keeping all these points in mind, just I'm making use of this empty space so that you can easily understand. So here I'm writing or trying to find the probability of the event Bn given A has already been occurred. You can apply the conditional probability formula here. That is, can anyone tell me conditional probability formula here directly? So probability of
Bn intersection A.
Very good. By
P of A.
probability of occurrence of
P of
event
A.
A, right? So this information we have now. So we also try to find probability of occurrence of A given Bn has occurred. Again, apply the conditional probability formula. So it is easy for us. So it is probability of A intersection Bn by probability of occurrence of the Bn event. So this is the second equation that we have. Now, I hope we already know that P of A intersection B is obviously equal to P of B intersection A. Am I right? So
Yes,
this
sir.
rule,
Yes, sir.
this rule I'm going to make use here. That is, from this two or from this second equation, I'm going to write the expression for probability of A intersection Bn. So that is simply a product of probability of A given Bn multiplied with probability of the occurrence of nth Bn event. So this is equation 3. Now see here, I have given the expression for probability of A intersection Bn from this equation 2 as a product of these two quantities. So since intersection is satisfying the commutative property with respect to the probability also, so this is also equal to probability of Bn intersection A. And this probability of Bn intersection A, you can see here in equation 1 in the numerator. So I'll be using that in the next page. So I'm going to shift the page, empty space. So probability of occurrence of the nth Bn event given A is probability of Bn intersection A by P of A, what we have already written. And in place of this numerator, I'm going to write it as probability of A given Bn multiplied with probability of Bn. This I will again show you. So this equation 3 I have used in equation 1 in the numerator. Okay. And denominator I'm going to write as it is. So this is equation 4. Now, from the concept of total probability, for the same situation, we have calculated the total probability. That is P of A for the same case. So here this can be represented as, if you can remember, 1 to n P of A given Bn multiplied with P of Bn. This we have already proved, already derived. If you can remember, this is the result we have derived in total probability. I will show you once again. Yeah, can you see this? This we have already derived in this
Yes.
case. Okay, so this result of total probability, I'm using the denominator of this Bayes theorem conditional probability. So therefore, this probability that we have the occurrence of Bn given A is simply written as probability of A given Bn multiplied with Bn, probability of Bn, by substituting the total probability. We have the similar expression but with a summation, because I'm talking about total probability. So this is what I have given in the previous two slides. So this is the final expression in a general case. I will show you once again. So this is what I'm trying to prove for a most general case of a sample space where we have n number of events, mutually exclusive events, and I have one embedded event A in this sample spaces which is overlapping different B's. So got it? So any doubt till this point? Any doubt till this point? We'll go for a most general case of a very good example of applying this Bayes theorem. I hope I already told you about this in the last class, right?
Yes, sir.
Yeah. So when I'm talking about this COVID-19 tests, so we have different types of COVID-19 tests here, and you can observe here that the test accuracy is very much important. Am I right or wrong? One second. Yeah, the test accuracy is very much important, and the accuracy depends on two quantities, like two properties of the test. That one is the sensitivity and the other one is the specificity. So the most important point with respect to the sensitivity is that, for suppose, a person is having the symptoms of, not symptoms, he knows that we know that he's having complete symptoms of COVID-19, right? So the person is having all the symptoms of COVID-19, and now he has come to the test of this COVID-19. Now the test is more sensitive. The sensitivity of the test is high. I'm saying that the sensitivity of the test is more or high. So that means the person who is having this COVID-19 will definitely test positive in that test when the test accuracy of the test is having more sensitivity. For suppose, let us take the opposite case. The test he is having less sensitivity or low sensitivity. Then a person having the COVID, when he goes for a test, then there is a problem of showing that person as false negative, right? Maybe if it is having low sensitivity for that specific test, it may give a result of negative for a person who is already having COVID. So such type of examples, we can treat them as false negatives. Okay, so definitely every test, whatever we are going to uh, perform here for finding the whether the person is affected with COVID or not, we should have high sensitivity so that it definitely detects the person as a positive person. Otherwise, if it is having low sensitivity, there is a very huge problem of giving false negatives. Actually, he is positive, but he is being given as negative, which is a dangerous situation. So we call those situations as false negatives. Similarly, we have one more property that with respect to different tests of COVID-19, that is specificity. Specificity is going to give the information about, like, for suppose, if the test method which we are following here is having high specificity, then if the test is given, if the test result is positive, it means that the person is positive. It is true that it is person is positive. Okay. Now here, for suppose, let us discuss the opposite case. That is the test which we are performing here to find whether the person is COVID affected or not. It is having low specificity. Then Low specificity in the sense it is going to give positive, but for suppose the person is disease free, but his result is being shown as positive, we call that case as a false positive. So these are the most dangerous cases. These are the most dangerous cases, right, when we are discussing about the COVID-19 test accuracy. So one, the test, if it is having low sensitivity, we talk about the danger of showing the false negatives. And if the test is having low specificity, so here there is a danger of representing this false positive. Okay, so keeping these two properties of this COVID-19 test in mind, so I'm going to proceed for the next one. So shall I proceed for the next one, or do you have any question here?
No, sir, it's clear.
No,
Yeah,
sir,
good.
it's clear.
Good, good. So I think you all know that we have two types of tests, right? Am I right? So one is a genetic test, the other one is a antibody test. And this genetic test, you already know, this is famously known in the short form like RT-PCR, so which stands for reverse transcription polymerase chain reaction test. Okay, and the other one is a antibody test, which is going to check the antibodies which are being given by the immunity system of the person. Now talking about this genetic test, so this is a nuclear derived test or method which is going to take these nasal swabs. You can see that, so the nasal swabs for detecting this presence of this virus inside this. And these tests will definitely have more specificity. That's what it is needed, right? And for suppose, even though they have more specificity, assume that the sensitivity is less. That means we observe false negatives here. So both are important. Both the properties of the test are important. So we observe false negatives. So for suppose here, this is trying to give the information about the antibodies which are being developed by the immunity system. And it will also check the antibodies which are being developed in the past. And this test is also having property like whether the person can withstand after he's been affected with COVID positive and his treatment is complete, right? And he is not COVID positive now. That means not having any symptoms after some medication. So all this also, this test, antibody test will give. That means the antibodies developed before COVID, and whether the antibodies will withstand or the process of developing antibodies within this person after the medication of COVID positive. Also, this information will be given by this antibody test. Now, so let's apply this Bayes theorem, the concept of Bayes theorem, which uses the conditional probability to test a specific case of a person who is tested positive. That means a person already tested positive, whether he is really having COVID or not. So this case I am going to discuss in this class. Got it? Probability that a person is already tested positive, right? It doesn't mean that a person tested positive is surely having a COVID. That depends on the properties of specificity and sensitivity. So we are checking whether the probability that a person who is tested positive is really having COVID or not. So this case I am taking here. Now see some specifications I have given you. One is COV representing that a person is having a COVID-19, right? It is representing COVID-19 virus. DF is representing that the person is disease free. The symbol plus is representing the test positive, and this minus symbol is representing the test is negative. So using this four, I have defined four types of probabilities. One is what I have already told you, that is the person has tested positive in the COVID test, and we are trying to find whether the person is really having COVID or not. That is the probability of a person having COVID or affected by COVID given he has already been tested positive in the COVID test. The second probability is the opposite case, like the person is already tested positive in the COVID-19 test, but here we are checking the probability that person who is been tested positive, whether he is disease free or not. Similarly, these two you can easily understand that a person tested negative, but what is the probability that person having COVID virus in him, and a person who is tested negative and he is disease free. So these are the probabilities that you can find using this Bayes theorem. So this is a very good application of Bayes theorem, and I'm going for the one of them, right? I'm going for the first one. Remaining you can check it later for a given problem. So here I'm going to concentrate on finding this probability that a person who is already tested positive, whether, so what is the chance, because I'm talking about probability, so what is the chance that he actually have the disease? This is what we are trying to find. So simply, first I will do one thing. So I will apply the conditional probability formula now. So it is P of, tell me, conditional probability.
COV intersection.
Or you can directly go for applying Bayes theorem. Already we have here, no problem. Anything you can go for. So then I'll do one thing, because already we have proved this or derived this for a most general case also. I will apply this Bayes theorem here. So this will be now A and this will be B. Based on that, you please apply it. So then in this case, this will be B in the sense it will be positive given
COVID.
is COVID. That means this means that a person, he knows that he is having all the symptoms of COVID, right? So a person having COVID virus in him, and what is the probability that the test gives a positive? A person already having COVID, what is the probability that the test gives a result of positive? This is what the meaning is. So multiplied with probability of A in the sense, it is the probability of being a COVID person, and probability of B, that means probability of being a person being tested positive. Now, tested positive in the sense, here we need to understand two cases. So one case, what I can tell here is a person, that is I'm talking about case one, a person is already having a probability, I mean I'm talking about like already having COVID and tested positive. This is one type of having COVID positive. Another positive is like a person, okay, I'm going to remove this A. So the another case is a person who is disease free, okay, but that person who is disease free, whether the test gives a positive or not. So finally, this denominator, what I am talking about is the total probability of being positive. So now we have two cases of a person being COVID positive, tested positive. That means he may have a virus and he is tested positive. The second case is he is not having any virus inside him, but he is tested positive. So all these changes are because of basically the two properties which I have already discussed, that is having low specificity and low sensitivity. So we should definitely check about these two properties when we are going for a specific COVID test. So now applying the concept of total probability. So this also gives the probability that he is tested positive. This also gives the probability of being tested positive. Therefore, the denominator, what I can write here is, so numerator I am writing as it is, and denominator, it will be representing the total probability that this is, the person is COVID positive and tested positive, and the person is disease free, but he is tested positive. So this is all about the total probability in the denominator. So any point, any question here you want to raise here? Just we are trying to apply the Bayes theorem, and we have applied the Bayes theorem. Later, denominator, a person being tested positive, we have two cases. One case, person is already COVID affected, and now we are talking about his test, whether it is positive or not. In this case, we get a positive. There is a chance of a person, disease-free person, he may also get a positive result. So this gives the concept of total probability of being positive in the test. So like this, the denominator has been modified. What is the time? 12:44. Okay. So now let's solve this problem. I have already discussed about the concept of sensitivity and specificity, right? So these values of 95% and 99% are giving the information about the test the person is undergoing. So the COVID test, a person who is undergoing is 95% sensitive and 99% specific. And this 1% prevalence is talking about the people affected in the population. For suppose 1% means for every 100 there is a 1%. So for every 100 population there is one person who is affected by COVID. This is all about the information given by this 1% prevalence. And the test is 95% sensitive and 99% specific. Now, am I audible? I'm going to erase all this in this slide. Am I audible?
Yes, sir.
Yeah.
Yes, sir.
Yes, sir. You're audible.
So we are trying to find the specific case of a person who is tested positive, whether he is having COVID or not. So the result of Bayes theorem, we have the formula that the person who is positive being tested positive and the total probability of being tested positive. This I have already written in the previous page. I am writing it here again. And also there is a probability of a person being tested positive even though he is disease free. Now, so we have to substitute different values for these probabilities based on these three values. First thing, I am talking about 1% prevalence. That means for every 100, there is 1% who is affected by COVID. So I'll change the color so that you can easily understand. So now, so this 1% prevalence information can be substituted here. You can see that here. Am I right? You can substitute here. You can substitute here. So now tell me, anyone can unmute and tell me what is probability of disease free and what is probability of COVID, a person having COVID. You have to tell me from this. You can tell in terms of percentage, no problem. From this information, I can.
So probability of disease free is 99% and probability of COVID is 1%.
Exactly, because the 1% prevalence is there. So probability of disease free is 99% and probability of person who is affected by COVID is 1%. So therefore this can be written as 0.99 and this can be written as 0.01. So I'm going to substitute those values. So here it is COVID. So this will be 0.01. So this value is not at all written up. Plus, and this value here again we have the same. So this will be 0.01 and 0.01 and disease free it is 0.99. Yeah. Now talking about this sensitivity and specificity. So based on these two, what is that information you can give? Tell me. Specificity. Let me tell specificity. let us talk about specificity, then we go for sensitivity. Once again, I am reminding you, if the test is having high specificity, that means if the test gives a result of positive, that means he is really positive. That is specificity. If the test gives a result of positive, that indicates he is really positive. That is high specificity. So this information of 99% of specificity, where can I substitute?
P of plus by COVID.
Is that here or here? Sorry. I'll go back 2 slides once again. See here. Yeah. So here, when I'm talking about sensitivity, I have told you that a person having all the symptoms of COVID, that is, he knows that he is having COVID, right? When he go for a test, if it gives positive, that means that test is having high sensitivity. Got my point? A COVID person, see here, we have 2 points. A COVID person going to a test, if it gives positive, that means that the test is having high sensitivity. This is related to the sensitivity point. Specificity. A person is tested positive in a test. He doesn't know that he is a positive COVID positive person. The test has given a result of positive, and the test, we know that the test is having high specificity. That means definitely that person is truly positive. Here in this sensitivity case, we know that he is a COVID person and he is tested positive. In the case of specificity, he doesn't know that he is COVID. And if the specific test is having high specificity and the test given a positive result, he need to accept the result that he is truly positive. Any confusion here? Here we know that we are COVID and we are going for a test. Whereas here in this case, we are not knowing that we are COVID affected and we are going for a test. Got my point?
Yes, sir.
Yes, sir.
So,
Sir.
yeah. So applying here, if you can see that this is P of plus, that is a person who is disease free, but he is tested positive. That means that can be related to the specificity, because it is not 100% specific. See here, this is not 100% specific. There is 1% lag in its specificity. Got it? So therefore, in place of this, I'm going to write what is the value that I can write here. Tell me. A person who is disease free but tested positive. Tell me, what is that value that I can write?
0.9.
Yeah, coming. It is 99% specific. There is 1% lag. So that 1% lag is what is this problem. So therefore, 1% lag value I am going to write here. Next, sensitivity. It is 95% sensitive. That means the person who is affected by COVID is being tested positive, and that test is having a 95% sensitivity. So therefore, here I can write 0.95 in place of this. And the same value you can substitute here. Can anyone tell me what is this simplification? 0.95 into 0.01 by 0.95 into 0.01 plus 0.01 into 0.99. Can anyone please calculate and tell me the value? Anyone can give me the value? I have the value with me, but you need to do. Are you doing it?
Yes, sir.
Yes, tell me.
0.010.
0 point?
01.
Check it once.
So 0.489.
Right. It is 0.489. Maybe I can approximate that to 0.49. Okay. Because it is very near to 0.4. I can approximate that to 0.49. That means a person who is tested positive, and the probability that the person, whether he is really COVID affected or not, is for these values of the test, that is 95% sensitive, 99% specific, and the prevalence is 1%. So the probability it was being calculated as 0.49 approximately, or I can go for 0.5, 50%, or I can go for, so this is representing 49%. So I can approximate that to 50%. That means for every 100 we observe, a test will give a positive. Am I right? And why? Even though I have a question, even though these tests are having high values of specificity and sensitivity, why it is this concept of a person being tested positive and whether he is having a COVID or not, it is giving only 50%. Why not it is around 90% and so on? Even though, did you get my question? Even though the tests are
Yes,
having
sir.
high sensitivity and high specificity, right? So the probability that a person is really COVID when he is testing positive, it is giving only a value of 50%. Why not a very high value? So did you get my point? So what may be the reason? It is giving only 50% probability. That is, can you see this yellow color? Not yellow, right? What I'm trying to show is some information which I didn't talk about the test. Sensitivity and
Yes, sir.
specificity will talk about the test, okay? But the concept of prevalence, this I have taken a very least value. We don't know the actual value of the prevalence here. Just I have taken as an example. So this low value of probability is not because of this sensitivity and specificity. It is all because of the low prevalence we have taken. 1% prevalence is very less with respect to the population. Sorry, very high. Am I right? Not very less, very high. Because for every 100 we are having a COVID positive. That means talk about 130 or 140 crore population now. So this is going to, this low result is because of this prevalence. So like this, we can have this Bayes theorem being applied for such a real-time cases. Maybe this is the last slide. Yeah. So with this, we close today.